hope all of you can see my screen. So let's say you have three stocks or two stocks, x1, comma x2. Their prices. And you want W as, so let's call it X as x1, comma x2, and W as the weight. Let's say small w, the W1, comma W2, where you know that W1 plus W2 is 1, right, guys? So your current Y is nothing but W1, X1. Just give me a minute. So plus W2X2. Okay. So understand this very carefully. See, all this is linear algebraic representation, right? So that's why we will take this opportunity here to write everything in linear algebra format. Please let me know if you cannot see. So W is nothing but looks a vector like this. Looks like a vector like this. I'm writing in Excel because it's in vector format. So I will color it this. So this is W2. W. This is W. This yellow thing is W. And so when we say W1 plus W2 is 1, that means if you multiply that with this as a transpose, then it will be what? The output will be W1 plus times 1 plus W2 times 1, W1 times 1 plus W2 times 1 is equal to 1. So you can write this equation as, this equivalent equation is W transpose, you know transpose, right? Transpose, or you can say, yeah, W times 1 transpose, doesn't matter. Where 1 is nothing but, you can say like this. So it's W times 1 plus W2 times 1. So W times 1 transpose, W is a vector, times 1 is a vector. We can make it bold, is equal to this must be 1. And here, this one, Y is equal to W1 x1 plus W2 x2 same. You can say that W times X transpose. All of you got it, guys? Yes or no?
Yeah.
Anyone else having problem? So Y is equal to this. Okay. So now what do we have? So we have covariance of x1 comma x2 is equal to, let's call it sigma HTML sigma. Okay. Let's call it sigma. So now the thing is that variance of x is nothing but, I can call it sigma 1 2, and variance of x1 is nothing but covariance of x1 comma x1, which will be sigma 1 1, and variance of x2 will be covariance of. Now, why this is true? That this is something you should. This is a homework. Variance of x is nothing but covariance of x comma x. So this is a homework. Try to prove it. Okay. Yes, Raghav.
Do you want us to just like tell you the answer next class, or if we just know after
You
we?
can take your time. Just know the proof, and you can just share it in the group once you're done. Okay.
All right. Do you want me to just tell you right now? Thought.
No, it will just delay it. Okay.
Okay.
If you know, I know you know. Okay. Like if you know the answer, I know you know. Do you get it? So, um, it's just for those who don't know. It's more important thing is to understand the paper. So let me just rewrite them so that you get more context. So now the question is that if we know these individual things, let's make it. Oh, let's make it this or make it blue probably. So the question is that this is given. So the question is therefore, what is the covariance of or the variance of y? Okay, this is the question because that measures the risk, right? That is the risk definition. So what we do? We do the basics. So variance of y is nothing but covariance of w1 x1 plus w2 x2 using this red comma, this same thing. The covariance is something like dot product of two vectors. So it will turn out to be covariance. So w1, w2. So take this one and take this one. So the first one will be what? Covariance of w1 x1 comma w1 x1. The second term will be covariance of this comma w2 x2. Third term will be w2 x2 comma w1 x1. The fourth term will be w2 x2 w2 x2. Right. So another thing you should do is covariance of x comma y is covariance of y comma x. So you will get here, this is nothing but what? It's imagine this is like dot product. So dot product of x1 comma x, so it's nothing but variance of x w1 x1. And variance is kind of you can think of like square, like the length square of a matrix. So since the length square of a matrix, the magnitude square of a matrix, this w1 will get out. W1 whole square times variance of x1, which will be nothing but w1 whole square times sigma 1 1. Okay. So this is what I mean by the mathematics. Similarly, here it will be w1 w2 similarly times sigma 1 2. Similarly, here it will be 2 1 and 2 1. It will be w2. Actually, it's nothing but w1 square is nothing but w1 times w2. W1 to whole square, or you can say w2. This one you can say times sigma 2 2. So when you add them, it looks like, so the sum is nothing but, because it's a sum, right? I wrote the individual term. It's nothing but like this. Now, this is an interesting term. Okay. This is something called a quadratic form. And the best part is that this the best part is how you write it. And this sum turns out to be nothing but something like this. This W1, W2 times a big matrix. So now I will write the matrix in form of a numpy array, okay? So this is W1, W2. And then the matrix will be a numpy array. Let's say I will write as, the first one will be sigma 1, the second one will be sigma 1, 2. This is the first row, and the second row will be this. This is the matrix times now this transpose. This will now look like transpose, like row vector. So if you want to visualize this, it will look something like this. Okay. And now W1 transpose will be what? Here it will be W1, here it will be W2. It's a transpose, right? And here it will, let's delete it. So this is W sigma. So this is what we call the covariance matrix. Okay, this is what we call the variance covariance matrix. This is what we call the variance covariance matrix, or often we call the capital sigma. Okay. So this tells you together not only the variance but also the covariances, that is of the x1 comma x2. So instead of writing this, what we will write is this is this. So this becomes redundant. Got it? This becomes redundant. Becomes redundant. So a pair of vectors, yes, Raghav.
So are you writing on the Google Doc?
Oh yeah, sorry. So yeah, so what I'm saying is this becomes redundant. So we just define it by this matrix. So x1, x2 is some random variable with means, you can say, we didn't write the mean. Let's say we have to write the mean. So let's write it. Mean we say mu1 comma mu2, and variance we say sigma. And in general, x1, x2, dot, dot, xn, we said together they are random variables. So same way, because each one of them has a different mean. So and variances. Okay. And when you calculate, the question is that what is the variance of, what did we get? This is nothing but the variance of W sigma W transpose. And that's what you see there in that equation. So what is the variance of W Wx transpose? That's what you got here, right? Wx transpose Y. The answer is W sigma W transpose. Simple. Okay. That's how you do it. Yeah. Yeah. So this is, yeah, Raghav.
Sir, so in the paper, I understood up until this part, but then when it went to the next part and talked about how you have to take the inverse of the covariance matrix and multiply that with the unit vector, could you explain that part too?
Sorry, I didn't get you. Can you come again?
In the paper, so I understood up until this part, but in the second part of this, it took the inverse of the covariance matrix and did some stuff with that, and I didn't fully understand what was happening. So could you explain that portion too?
I see. Okay. Just give me a minute.
Yeah.
All of you got it, guys?
Quick question, sir. Maybe
Yeah.
I'm making a mistake, but would it be like the first row, like if we write this properly, W1, W2 would be at the top, or no? Like, am I
Which one will have the top?
like the matrix? Shouldn't W1, W2 be above the covariances, or am I wrong with that?
So can you point? Okay. So let's, I think it's my fault. Let's make it, yeah, point out which line.
So it's G. You know how there's a picture.
Yeah.
Is W1, W2 supposed to be above the sigma notation ones, like the covariances and variances, or no?
No, it's like two matrices, like how you might do matrix multiplication. There is no
Mhm.
above or below.
Oh, I see.
It's it just looks like this.
Okay.
Just matrix multiplication. You know matrix multiplication, right?
Yes.
So it's like I wrote it like this because those are written like vectors.
Oh,
Like the same color means same vectors. That's it. And also to match the dimension. Like you see, it's 1 cross 2, then 2 cross 2, then 2 cross 1. So it's 1 cross 1, the output. It's a real number.
yes, sir. I understood.
And that's the real number is nothing but um, the final, um, because this y is also a real number, right? It's a single number. So the variance will also be a single number.
Yes, sir.
All of you understood this? Any questions? Shonin, did you understand? Shai Pratisht?
Yeah.
I know this is a mathematically a bit hard. Siddiq, did you understand? Okay, at least the idea. I think this two-dimensional is also okay to understand. Okay, go ahead. Please share your screen.
Okay.
Yeah, I will sometimes stop you in the middle to explain it, okay? Because it's
Okay.
important to understand.
Yeah. Right.
Go to the first page.
What?
Go to the first page. It's not over yet.
All right. Right.
So,
Yeah. Sorry,
go ahead. Go ahead.
Okay. So if we have 1 as n by 1 vector and sigma as our covariance, we get this. I'm not exactly sure about this.
Let me just.
I didn't quite understand it that well.
Okay, so they are saying that the solution comes out to be this mathematically. Okay.
Right.
Now you have to learn a bit about how to solve and find the optimization of that. That is not, I think, not out of the scope, but I think you should assume it right now. Okay, this is the minimum value of the W for which you get the minimum is this.
Right. So this is the minimum of W.
Yeah, so it's, you can see the
Ah,
whole idea is what, finding the weights W such that the risk is minimized, right?
oh, right. Right.
So the it's saying that the minimum, the W for which its risk is minimized is this.
Okay. Right.
Raghav, you are also, I hope you understood what I mean, and others.
Yeah, I understand the general concept, but should we just as homework? Is it? Do you
So why
recommend?
don't you read the proof up online and present it next day?
Or
Okay, does that sound good?
yeah,
Uh,
Any questions out there? So you can write down the homework. So I hope you will remember, or should I write it down for you?
uh,
I I can write it down.
Okay, can you write it in the group, WhatsApp group?
Yeah, sure.
Okay, go ahead, Shonadu.
okay. So we don't know the covariance matrix, so we have to replace the sigma with the sample covariance. I know it doesn't have it with the replaced covariance. There wasn't enough space on the slide.
No, it's okay. Don't worry about it. But I hope all of you know how to replace what is the what how do the replacement comes, right? How do
Yeah.
you find the sample covariance?
Hmm.
You
Okay.
know, right?
Uh, actually, no, not that well. I don't
Okay.
know how is it unknown, really. I'm sorry.
Oh, okay.
This thing
Because
GMV is I didn't quite get it that well.
okay, let me explain. Yeah, so why I'm doing this with you, because I want you to go into as much details I am going to, okay? Because that's the
Okay.
whole idea you're doing this whole research program, right?
Right.
So yeah, I will just take it over a bit.
Right. So it
So
is.
for example, yeah, because this is common to portfolio optimization, so that's why I'm doing it. Um, so the question is that all these are random variables, right? So what is a
Right.
random variable? A random variable is, what is a random variable?
A
A random
variable.
variable, yes,
A variable that can be anything.
yeah, that can take is a variable that can take many values,
Okay.
that can take multiple, like quantum thing, okay,
Right.
like multiple values. So the question is that how do you define it then? Okay, that's a simple question.
Hmm.
Because as the stock price tomorrow can take multiple values, right?
Yeah.
So a stock price tomorrow is an example.
Okay.
So the question is, how do you define it? So we define it like this. We define it that a random variable can take multiple values, but each of them or the values around it has certain probabilities. Okay.
Okay.
So if you think about what I did on the first day, and wait, let's see. Yeah. If you remember this, I told that each one of this is a random variable, right?
Yeah.
So let me copy this Let me show this picture with you. This one. Each time point is a random variable, right? Like this, something like this.
Right.
So what I'm saying is, that's,
Um, sir.
yes.
So these values are probabilistic. Like, just wondering if that's the actual word.
Yeah. So what I mean
Okay.
by probabilistic is that a random variable is a variable that can take all the values. Okay.
Yes, sir.
But each value has something else attached to it. Like a
Mhm.
normal function can only take one value, right? Output.
Yes.
But here it can give multiple values, but we'll give probability to it. So each value, let's say it can take x1, x2, like it can take 1, 2, 3, 4, 5, dot, 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 any natural number. And we define a probability P of I, which is 1 by 2 to the power I. Do you see the point? This is one such probability. This is called a geometric probability, it's geometric random variable. Okay. This is a geometric random variable. And it can take only these values. It's a geometry, and you can see, we can actually prove that sum of pi is 1, because the geometric sum you can prove it's 1. Okay. So a random variable can take this, but also it can take real values. Like continuous, this is discrete. But it can take continuous values too. Then it's tricky. Then in that case, it doesn't, and I wrote it here actually. In that case, it takes a probability density f of x. Okay. Takes a probability density f of x. And I wrote it that in that case, we measure it by the density, but the density doesn't mean, for example, as I said, the density doesn't mean, for example, in this case, it's a density, right? And you can, sorry. And you can see it's taking values 20. So density doesn't mean that it's a probability. But what does the density tell you? The density tells you the fx dx is a probability that it will take value in that interval. Okay, it doesn't make sense because there are infinitely many values, right? The probability of taking any point is always 0. But hence we always say probability inside a region, not any single point for continuous random variables. That's important. Make sense, guys? Yes or no?
Yes, sir.
So could you just explain that last bit one more time?
So what I said is that just give me a minute. I'm finding a good picture for you guys. So what I'm saying in that in this case, in the continuous case, we say that we do not say probability in a continuous case. We do not say that it is a probability at a point, because among infinitely many values because it's a real number, the probability of taking a single value is always 1, is 0, right? So it doesn't make sense to say probability of a continuous random variable like is at a point 1. But what makes sense? So it doesn't make sense to ask what is the probability of a continuous random variable, that is a random variable that is changing or that can multiple values, to take a value at a certain point x. Doesn't make sense because it will always be 0, right? Because it will be always be 0. So what does it make? So we define it in terms of what is the probability it will take value in a certain interval a comma b. That's how we define it. Okay. And that can be found out, like first we define in terms of this, that probability it will take x in small interval x comma x plus dx, like around x, that means around x, it's nothing but fx f of x dx. This is the probability that I have written over here. The f of x dx is the probability of x taking values in this small interval, but doesn't make sense to take value at a single point. And in general we say that if x is taking values in a comma b is this. So let me is this. Yeah. Let's see. Probability of x taking values in a and b is nothing but integration of fx dx. So fx dx, as I said, is nothing but probabilities of taking values around x. So we change x from a to b and integrate it. So this is what it turns out to be. And of course, the integration from all the, since it's a real number, it should take minus infinity to infinity values and it will turn out to be 1, the integration. So this is all about random variables. Did you understand, guys? Siddiq
Yes,
and
sir.
others? Okay. And finally, it comes out the whole idea of covariance. So covariance is nothing but it measures. So as I said, so when you said random variable, it's like random, we don't know. So let me first explain covariance. It measures the relationship between two random variables. So it says a covariance of x1 comma x2. Okay. Before I move covariance, the next thing is how to define, how to understand a random variable without randomness. Okay, so what are integrals? It's a very good question. So integrals are this. So you can say integral is nothing but, let me find a good picture. Yeah, this is a great picture. Love it. So integral is nothing but an area under the curve. You can say. So integral is area under integral of a function is area under the curve of the function when you draw it like this. So integral of 0 to. So similarly, probability is nothing but this curve. Let's make all this smaller so that can, yeah, it's the area under the curve of fx. Okay, area under the curve of fx. This is what the integral. Did you understand, Siddiq?
Yes, sir. Thank you.
Okay, all of you understood? Any questions?
No, sir.
No.
Yeah, sir, is this like a reverse derivative?
Yeah, you're right. So it's a reverse derivative. Derivatives breaks up into pieces of the functions, and you can say this is, and this that is captured by something called the fundamental theorem of calculus.
Sir, I
Yes.
just noticed one thing. If there's a way, sorry, I just need to. Can you post like these notes? I can't find them. Are they on? I can't find them on the WhatsApp group. These like the things you typed out. Can you post them
No,
in the?
this is no. I have not I have not typed these notes before, right? So I'm typing it today. So I will share it with you,
It's just I can't find them anywhere. That's all.
or I will share it with you today. Okay.
Okay, thank you.
So
Sir.
do you want to access it right now?
Just like after the class, I can review the stuff.
So you want to refer to these notes while like right now in live in
Yeah.
class? Okay. Let me share it with you. So I will call it probability notes.
Thank you, sir.
Sure, I will share it with you right now
Um,
in the group in that chat.
thank you.
What is happening? I have shared it. Please check if you can access. Okay. This is, you can sort of call it like a crash course of, and I'm going to reverse when that's fun actually. I'm going in a
Yes, sir.
reverse way because I'm motivating it by this problem. Can you send a picture of the paper? So I am kind of motivating it by this. Just give me a minute. By essentially this one. Can call it motivation. Okay, so this is a motivation, and we are trying to explain it from bottom to top, top to bottom. So we are taking a problem, we understood it, and now we are understanding the depth. So as we have said that a density is a probability distribution, and we are discussing the probability distribution, and integration comes up naturally because this thing is important, that the sum of probability should be 1 because it's kind of distribution, right? So when here integration, the sum in, and as you can see, sum in continuous aspect is integration, as you can see here. And thanks for Siddhi for asking the question that You can see a sum as integration over those small regions, okay? And when you add them up and make those regions smaller, you get the integration. That's how it's defined. And that's done with this, that's defined with this limiting. But yeah, let's keep it. But I hope you understand the idea, guys, right? So all of you on the same page with this? Yes or no?
Yes, sir.
Okay. Um, okay, so the next one. So naturally, the question is that, so we understood the integration is this. The next thing that is important is to understand that natural thing is that, okay, I do not know what value it will take, but there should be some component of non-variance, like constant. There should be some, like for example, if I say that a coin has 60 or 80% chance of falling heads and 20% chance of falling tails against a coin which is 50-50, there should be. So for example, if we take a coin that is that actually that gives 80% chance of heads versus 50-50, 80-20 chance of heads or odds versus 50-50, we are trying to find simple deterministic, not random, deterministic measures of randomness. Do you see the point? Like we are trying to find measures that tells you how random it is or information about the randomness. And that's where the comes mean and variance. Okay. Or we call it, there are many dispersion and centrality. That means a central behavior and dispersed behavior. So you can think in terms of like a dartboard. Like this. I can think in terms of a dartboard. That's large. Okay. You can think in terms of the dartboard and you can kind of see that. Okay, so let's try out something. Let's insert drawing new. Yeah. So you can think in terms of like this as kind of the far away thing as kind of dispersion, how much dispersed it is. Okay. Like how much dispersed it is all over. And like how much, so what should I say? I hope you understand what I mean. How much dispersed it's all over, like how much all over it's dispersed. And you can say that the mean is kind of how much the average of it. Like where is the mean here? It's like a kind of the median of the points if it's in 2D. Like the median is how much, yeah, the median is a median point. So we can say that the way it's all over is that. So that's what I'm trying to make you understand here with this example. So think in terms of a dartboard. Okay. Yes. Questions? Yes. Siddiq, Saidriti. Yeah.
So you know how you just said there would be a median in this dartboard.
Yeah.
Would that just be one single point, or would that be like a ring going around?
It'll be one single point. As I said, these are all deterministic.
Okay.
So it's centrality, you can so call it. Like there are many ways. Median is a centrality way. In variance is not only yes, there can be range. You can say that how much disparate it is. It's like a range of values. It's like a range, maximum, minimum. So there can be multiple ways. Other things are there. Interquartile range are there. Many other measures are there. But the whole, you have to understand that why they are doing it. It's kind of, you can say that this is kind of in return and this is kind of in risk. Okay, you can say the mean is the return and the dispersion is a risk. Okay, you can say that. Um,
Thank you, sir.
yeah, and this is the entire idea, I would say. And the whole of probability is trying to understand and find those measures, a non-random deterministic things that are helping us understand the random variable. Okay. Um, yeah, because we will use those to take our decisions. Yes, questions, Saidriti and Arnav. Saidriti first.
Sir, would the variance also, like, could you also represent that with the standard deviation?
Yeah, so standard deviation is root over of variance, square root
Yeah.
of variance.
Okay, thank you.
Sure. Arnav?
So I was just wondering, do we need 80-20 odds? Or can it be like a different number?
It can be anything. So what I'm saying is that I gave two examples that those probabilities, okay, if two probabilities are varied, see, the thing is that it's both both of them are taking, both of them are variables are taking heads and tails, right? But different probabilities are there. So the whole goal is, can we find out values that can help us distinguish this difference based on those probabilities? So therefore, mean is defined as, you can say, sum of xi and probability of I, okay, overall I. And variance is kind of sum of, or you can say in discrete, so you can say we denote it like expectation of x. And variance is sum of how much xi is moving, or you can also show it as mean, mu. That's why I use the whole idea of mu. Um, let me see where I wrote mu. And similarly for the variance, we use this. So we are seeing how much variance it is. So essentially variance is nothing but, okay, there is a 1 by n over here, average. So similarly here, that how much each of the xi is changing from the mu, is changing from its mean position. That means it's measuring the um, the dispersion. It's like how much it's changing from the mean, that is a mu, each of the points, and we call it sigma square. Okay, and this too actually captures most of return, like the average and dispersion, and that's the whole idea, right? If it takes a large number of values, it has variability. That means it's not a single number. Do you see the point? So that's what the whole idea we're trying to understand. If it can take large number of values, we will whether understand it by two numbers, not one. This gives there are other things like skewness and other things. Okay, skewness and other things, but these two are etc etc. But these two are the major things which tells you. Did you understand, guys? This is a univariate. Like these are univariate measures of a single random variable. Any questions, guys? Arnav, I hope the doubt is clear.
Yes, sir, it is clear. I understood it now.
Super. Now the next natural question comes. There are two things. One is univariate relationship, but also probability and statistics and data science about relationship between two variables, right? Like if you want to understand how two stock markets are moving together, how two images are similar together, or multiple things, how data are related to each other. And that's why we define measures between these two random variables, covariance. So you have to understand also, I like you to use this kind of expectation. So you can see this is nothing but you can write it as expectation average of x minus mu, you can say, whole square. You can also write it like that. Okay. And if you expand it, this is your homework, show that. So this expectation is nothing but linear. Remember that. This expectation is linear. By linear means expectation of ax plus b is expectation of x, just like average works plus b. Here a is here. Similarly, expectation here in this case, so you can see how it is, right? Here it's okay, I missed something, pi. So here you can see 1 by, so essentially you can think of this like as a placeholder. Okay, this is a placeholder and this is a placeholder. So in this case it's just xi pi, so x is the main thing, pi is always constant, and in this case it's xi minus mu whole square. So you can see that's xi minus mu, x is coming there. So x can take all the xi values, so instead of x we are taking xi and pi together and replacing in the function. So you can show that this is nothing but x whole square minus, minus mu whole square, mu square. Often this is also useful to think about. So it's your homework. This exercises are helpful because it helps you just deal with the basic math. But the whole idea is understand the philosophy, understand the why we are doing this, because it will help you think that we want to find a deterministic representation of randomness, because it can take multiple values. So we are finding a deterministic representation. Similarly, covariance of x1, y1, x1, x2 is nothing but, as I said last day, what is the meaning of covariance? I have explained this last day, but let me explain it once again. I think I explained it. Do I have those notes? xi, yi. Let's see. I think I might have them. I think I explained the covariances with you guys, but again, let me explain it once again. Yeah, I probably used this diagram. So, okay, there's a fundamental difference, and this is why statistics is important. I will come to this again, but let me explain it. So, covariance is nothing but we want to measure covariance wants to measure how covariance between x and y wants to measure that how x and y move together. Okay, this is important. How x and y are moving together. So like R is when x increases, does y increase or decrease? And similarly, like, okay, or decreases. So these are the kind of questions we want to understand. To understand, what we do is we first change everything, change x to, or you can call it x1, y1, x1, x2. Change x1 to x1 minus its mean. Let's call it mu1. So understand, yeah, mu1. And similarly, x2 to x2 minus mu 2. Now, what this does, it helps you understand irrespective of whether it's irrespective of its mean. So when we change it, we get a graph something like this. Okay. I will move it probably here. We get a graph like this. Now what happens? Now let's understand the question. We want to understand how x and y moves together. So understand that the region, the first quadrant is x1 greater than 0 and x2. Let's assume x1 and x2 are x and y axis represent. The second quadrant is x1 less than 0 and x2 greater than 0. The third quadrant is x1 less than 0 and x2 less than 0, both, right? And the fourth quadrant is x1 greater than 0 and x2 less than 0. So you can see the first is both are moving in the same way, the first and the third. And here it is both are moving in the opposite way. Right? So what we're understanding here, this is something very important. We are understanding that, so therefore one way to is, we also it matters, value matters, right? So what we are doing is simple, that if we multiply, now we want to, again, the whole idea is to change everything in a deterministic format. So we want a single measure. So we multiply x1 times yi. Observe that x1 times yi is positive if the xi yi is in both first and third quadrant. And xyi is negative if they are in second and fourth quadrant. Did you understand this, guys? Yes or no? All of you?
Yes. Sir.
No, someone said no? Okay. I think all of them said yes.
Sure. Can this just be considered as like, in a way, maybe Audrey said this in a different way, but if they're on the opposite sides, it gives less return, less risk. But if on the same side, it gives more return, more risk.
You can say no. There is no return out here, okay? Because the return is for individual random variable. Okay, here's how they are moving together. So you can say if they are both moving. So you can say if xi, yi, if x1, y1, x2 are moving together, you can say that so it's not important. But if x and y are not moving together, what you can do, you can buy from one, buy that moves up, and sell that moves down. Okay, something like this. So yeah, and if x1 yeah, I think that's a way out. If both are moving in the same direction, that's not important because you cannot use. So this is something called arbitrage. Okay. I mean, you can say that buy x1 and sell minus of x2 if they are moving together. But essentially, I mean, if they're moving together, it's not really fun. Okay. Yeah. But yeah, this is arbitrage, means you can find those opportunities where, yeah, that's the whole idea. So that's one way of thinking about it. Did you understand, guys? Enough. But coming back to covariance. Okay. Coming on to covariance, x1, x2, let's remind ourselves that x1, xi times yi is greater than 0. So one way to do is that we sum all the xi's. If we sum all the xi's, it will tell you that, see, in this case, if we sum, there is more in first and third and less in this. That means what? If the sum is greater than 0, that means first and third quadrant has surpassed second and fourth quadrant. And remember, these are all mean normalized. Okay. That means it's all telling you how it's like. So if it's, that means it can also happen that there can be a lot of numbers, lot of points in the third and second and fourth quadrant, but they may be close towards zero. That also is a possibility, that there is not much diversification out there. So you can say if it's less than zero, that means the other way around, right? The second and third had taken over. Second and fourth has taken over the first and third. All of you got it, guys? This is important. Right? So what we do is, therefore, we define covariance as kind of average of this sum. So now remember, this xi, yi are mean normalized. So sum over xi minus yeah, there's a bit of an issue here. Okay, you can say okay, let's assume that it takes all the values xi, yi times yeah, let's call it x1i. X2i is all the values it can take minus mu2. Okay. So this is what the covariance of x1, y1 looks like. But again, the proper definition is this. So now we can see again into pi. Sorry, the probability of I have forgotten. Pi. Yes. There is a small thing over here. You can say pi because both of them have different probabilities. Understand that? Okay. So there is a small. Okay, one thing I have missed over here is this 1/n should not be there. Okay, this pi is enough. Sorry, I made a small mistake over here. Because this pi is if pi is 1/n, then it comes out. I made a mistake over here. In this case, similarly, this 1/n will not be there. It will be this. If all the individuals are 1/n, then it comes out to be. But again, here it should be. You should think about it very carefully. That why it's pi, because we are taking this in a together. So x1, x2, we are saying that it can take x1i, x2i with probability pi. Do you see the point? It's taking together values with probability pi. Make sense? So instead of now in a one-dimensional probability distribution, so bivariate probability. So let's see. So it's now, what is the bivariate probability distribution? So let me, yeah, this is what is a great example. Let's remove the term CDF, but yeah, I hope you understand now from this picture. Now each point is nothing but has a probability value. Got it? So this x1, x2 is nothing but xi I am calling. And similarly in continuous distribution, it will be something like this. In continuous, it will be discrete. This is continuous. But again, it's a multivariate. That's why multivariate calculus is important, which I'm not covering here, but I'm telling you the basic ideas. Okay. So this is the basic idea. Okay. And then you can write this as covariance of expectation of simple thing. No. Just like we did it before. Now the expectation, remember, is over x and xi, yi both together, not individually. Okay. We call it x1 minus mu1 and x2 minus mu2. Okay, this is how you define it. Got it, guys? Did you understand? All of you? Any questions? Yes, Raghav.
If the variables are random, so that like they are not related to each other at all, would the covariance be like close to zero or something?
Yeah. Again, I am one thing to repeat is that xi yi is considered jointly. That's why they're called. That's why they are called. It is called joint distribution. It's jointly, and yes, if x1 and x2 are not related, or we call it independent, or linearly related, to be very honest, then covariance is 0. That's true. So this is important to understand. So this is a kind of a brief crash course. So now this is where it comes now, that covariance therefore turns out to be, so now multivariate. So this is x1, x2. When I said x1, x2, as I said, x1, x2 is itself a random variable like this. Now naturally the question comes that what is the expectation of it? So that's how we write this. That expectation, because we said that whatever random variable we take, it's always important to have a mean and a variance. X1 is mu1, mu2 dot mu n, and variance is sigma. Okay. So because we need all that for all the distributions. Okay. Let's see if we can have some more space. Great. Okay, so the next natural question, another thing is left, that is statistics. So where is statistics coming? Where is this estimation coming? We are finding this W, right? So the thing is coming is that we don't know the actual distribution. Like for example, the mean and variance are unknown to us, right? The mean and variance are unknown to us. So what do we do? Therefore, the goal is to observe the data. That is what we observe, like small, these are called realizations. Let's say M, we observe M data points. We observe it. These are called realizations. And then we try to approximate and find out those mean and variance, or we also call them parameters which are unknown to them. These are similar to the parameters in a neural network. Okay, this is similar to parameters in neural network or any other Markov chain, any other thing. So essentially, the goal is use data to find, so use probability to model the scenario. Like we are modeling the finance scenario, for example, we are using Markov chain to model a financial stock, right? Markov chain or probability distributions. And we are using the observed data to find out those unknown parameters which are in Markov chain. That is, can someone tell me what are the unknown parameters in Markov chain? Any idea? What are the unknown parameters in Markov chain? What do you think? A wild guess. What do you think is not known in a Markov chain and you are using data to find it. Yes, Siddiq?
So is it the weights?
What weights?
Like the like the arrows that we had I drew a diagram and then I had some transition probabilities. Like
Exactly.
weighted
The
arrows.
transition metrics. Very good, Siddiq. The transition metrics are not known and we are using data to find the values. Okay. And that what estimation, or rather the thing is that what is the best parameter value. So the modeling part is probability, and what the best parameter value is nothing but statistics or estimation or data science or machine learning, whatever you call. Estimation, you can also call the optimization. Okay. For example, the WIs that you're finding out for the portfolios are also our statistics estimation. It's an optimization. The weights in portfolios are estimation or statistics. Okay. Those are find out that method. For example, in Markov chain, the transition probabilities are found by averaging that specific scenario by total. Anyways, let's not talk about that because we have to understand it. But again, the basic thing is that statistics is used to answer what is the best parameter value, and probability is used to answer how to model scenario, and with unknown parameters. And what is the best parameter value for the model above? So this is the interplay of statistics from data. And of course, you also need data plus probability, how to model it, because you want the probability model to actually represent the data. So data is important. So under structure of the data, for example, the graphical model is a different model than a Markov chain model, right? A deep learning model is a different model, but again, both of them fit the data, the portfolio data. Similarly, the probability model is different there, and statistics model is different. Therefore, for each probability model, there is a different statistics estimation problem. But this is the entire idea of probability and statistics. Okay, that's what you're doing here. And when they are said that you're using if you remember that here it said that you're using the estimated value. So this is the difference. Using data, you can actually find out this. So as I've said, the sigma and the mu's, these are all parameters we don't know, right? So the sigmas and mu's can be found out using the data you have observed. And that's what we mean by sample covariance matrix. Samples mean the data, the sample of data you have observed, and the covariance matrix is if you use this data to find a good estimate of that actual covariance that you do not know, but with which you have modeled, then this is what you're getting. Yeah. Raghav.
Do we not know the covariance because it's from future stock market data?
Yes, we do not know the covariance because the stock market is future and it's a random variable. Okay.
So we use statistics to kind of predict what's going to happen, and then use that.
First, we use probability
Mhm.
to model it as a random variable,
Okay.
as an invariant random variable, all the stocks. Okay. So this RT, every time point, as I said, if you remember, every time point is a random variable, if you remember. Okay. Every time point is a random variable. So every time point in the future is therefore a joint distribution, okay, of n random variables. And those joint distributions is modeled by some mean mu, which is nothing but mu1, mu2, mu_n, and some sigma, that is the covariance matrix that I have shown you. And this is an unknown. You do not know that, right? So since we do not know that, as you have said, we use data and statistics to find these estimates. So these estimates are found by statistical estimation, as you can see. These are estimates. These are proxy. This is the best. For example, if I tell you that we do not know the mean, let's say I tell you that what is the average hour I teach I have a probability distribution that you do not know, because today I see I have crossed 1.5 hours almost, right? But other days I do 1 hour. Okay. 2 days I have done 1.5 hours, but other days, so I am a random variable. My teaching hours is a random variable. If I ask you that what is my average, we do not know my actual average, right? You do not know even my distribution. But if I tell you what is my average, you do not know it, so you approximate it. What do? You take the average of all the days of hours of the I have taught you, right, guys? Similarly, if you take, so that sigma has also its corresponding sample estimate from the data that you have observed. The data changes, that thing changes, right? So what it's saying is that from the data, this is the best estimate we have. Okay. And we use that. So the homework to next day is to find out why this happens. Why this minimum happens. You can try it out. Okay. This is important. Okay, guys, got it? Yes or no? All of you?
So is that for
Yes, sir.